Okay, so imagine looking up at the night sky, right? All those stars.
Yeah, countless. Billions upon
And
billions.
then realizing sometimes something from one of those distant systems actually like visits us, comes knocking on our cosmic door.
It's a pretty astounding thought, isn't it?
Yeah.
That thrill of discovery, especially when it's, well, completely unexpected.
And what if we could actually reach out and maybe not touch it, but get really
Well,
close?
that's exactly what we're diving into today. There's this, frankly, mind-blowing proposal
Okay.
to redirect NASA's Juno spacecraft, the one orbiting Jupiter right now,
Yeah, Juno. So redirect it. Where?
to intercept a brand new interstellar visitor. It's called 3I-ATLAS.
Wow. Okay, that is mind-blowing. An interstellar visitor.
It's an incredible opportunity for a deep dive, really. These are, I mean, literally pieces of other star systems.
Right. Traveling across who knows how many light years.
Exactly. And it's only recently, like in the last few years, that we've even started spotting them as they swing through our solar system.
So what can we learn from them? Why is this such a big deal?
Oh, the potential knowledge is immense. Think of them as cosmic time capsules.
From other stars?
Yeah, offering us these unique insights into how other systems formed, what they're made of, the conditions there, and, well, there's even a pretty thought-provoking idea about what some of them might be.
Okay, you can't just leave it there. We'll definitely get to that. So why is this specific chance with 3I Attilas so unique? What could Juno tell us?
That's the mission for this deep dive. Let's unpack it.
All right, so this whole field of interstellar visitors, it's sort of kicked off pretty recently, didn't it?
It really did. 2017, that was the year. The Pan-STARRS Observatory in Hawaii spotted the first one.
Oumuamua, I remember that name, caused quite a stir.
Huge stir. Yeah, it was absolutely the first interstellar object we'd ever confirmed. A real game changer.
And then there was another one fairly soon after.
Yep, just 2 years later, 2019, we got two at Borisov. That one looked more like a conventional comet, but still from another star.
Both amazing discoveries, but they passed through pretty quickly, right?
Very quickly. Fleeting glimpses, really. Which brings us to this latest one.
3IALAS, also known as C2025N1ATLAS.
That's the one. Detected really recently, July 1st, 2025.
By the ATLAS system Asteroid Terrestrial Impact Last Alert System down in Rio Hurtado.
Correct. So now we have our third confirmed interstellar visitor.
So beyond just the wow factor of seeing something from another star, what's the deeper scientific drive here?
Well, think about how we study our own solar system's history. We look at asteroids, comets.
Right, remnants from the early days.
Exactly. They tell us about how the sun and planets formed, interstellar objects. They do the same thing, but for other star systems.
So it's like getting a sample return mission without actually going there?
Precisely. You can learn about the elements in that system, maybe subtle isotopic differences that hint at how their planets formed, or find complex organic molecules.
Yeah.
It's like getting a piece of a foreign stellar nursery delivered right to us.
Okay, the potential is huge. But you mentioned they're fleeting. That sounds like a major challenge for actually studying them up close.
It's the major challenge. These things zip through the solar system incredibly fast.
So launching a new mission from Earth.
Almost impossible. The warning time is just too short. The researchers behind this Juno idea point out that, yeah, a dedicated Earth launch, or even something like the planned ESA Comet Interceptor,
Which is designed to wait for a target.
even that would be, and I quote, completely infeasible for catching something like 3I Attilas with its current trajectory.
Okay, so that makes this Juno plan even more interesting. Why does it work?
It comes down to what the researchers call a strange happenstance. Just pure cosmic luck, really.
Look at this.
3I Atlas path happens to be taking it unusually close to Mars, then Venus, and crucially, Jupiter.
Where Juno already is.
Exactly. That close pass by Jupiter is the key. It's a rare alignment for an interstellar object, giving us this unique window.
And who came up with this audacious plan?
It's a team led by Professor Abraham Loeb from Harvard.
Low. Okay, the Oumuamua guy.
It's the very same. He's teamed up with Adam Hibbard and Adam Crowell. They're both with the Initiative for Interstellar Studies, IFORIS, a UK nonprofit.
Has they worked on similar things before? Interstellar travel concepts or ISOs?
Oh yeah, they're deep in this field. Loeb's work on Oumuamua is obviously central. Hibbard has Project Lyra, which is all about developing ways to potentially catch future ISOs, or even Oumuamua.
Catch Oumuamua. Wow, that's ambitious.
Highly ambitious, yes. And Crowell was involved with Project Icarus, which was a design study for a fusion-powered interstellar probe. So, yeah, they definitely have the background for thinking big about interstellar targets.
Okay, so let's get into the nitty-gritty. How does this actually work with Juno?
All right, so 3ILES is set to make its closest approach to Jupiter on March 16th, 2026.
How close are we talking?
About 53.6 million kilometers,
Hmm.
or 0.358 astronomical units AU.
Hmm.
Still quite a distance, but close enough for this plan.
And the plan involves giving Juno a push?
A significant push. A delta V, change of velocity, of 2.675 kilometers per second.
That sounds like a lot for a spacecraft that's been in orbit for years.
It is. And they propose doing this main run on September 14th, 2025.
Okay, but there's more to it, right? You mentioned Jupiter's gravity.
Yes, this is where it gets clever. It uses something called a Jupiter Oberth maneuver.
Oberth sounds familiar. Like a slingshot effect?
Sort of, but it's more about maximizing the efficiency of the engine burn. They need to do an initial burn first, a smaller delta V, on September 9th, 2025.
September 9th. Wait, isn't that right before Juno was supposed to end its mission?
Exactly. Just 8 days before its planned deorbit into Jupiter's atmosphere. Talk about timing.
Wow. Okay, so this first burn does what?
It lowers Juno's orbit, makes it dip deeper into Jupiter's massive gravity well.
And then?
And then when it's moving fastest, deep in that gravity well, they perform the main burn, that 2.675 kilometers push. Because it's already moving so fast due to Jupiter's gravity, the burn is much, much more effective at changing its trajectory. That's the Oberth effect.
So it's like getting more bang for your buck, fuel-wise.
Precisely. It dramatically increases the final velocity change you get from the same amount of fuel. It's ingenious.
So it's not just about the science, it actually extends Juno's life.
Absolutely. It basically rejuvenates the mission, gives it a whole new, incredibly exciting target beyond its original end date. A huge dual benefit.
And the goal is for Juno to actually fly by 3I Atlas.
The goal is interception on March 14th, 2026. 2 days before ATL's closest approach to Jupiter.
Incredible. What kind of tech allows you to even calculate such a complex maneuver?
Yeah, you need some serious software for this. They use something called OIIT's Optimum Interplanetary Trajectory software for the initial calculations, figuring out the basic orbits and velocities needed.
Okay.
But for the really fine-tuned stuff, predicting the precise path and figuring out the minimum possible velocity change needed.
You need something more specialized.
Right. Hibbard actually developed custom software written in C. It uses libraries from NASA JPL, specifically the NAIF toolkit.
It's
Navigation and Ancillary Information Facility. They provide these super detailed data files called spicy kernels. They contain all the precise positional data for planets, spacecraft, everything you need for mission planning.
so really high precision stuff.
The extremely high precision. They also used other software called Nomad to integrate the complex gravitational interactions between Juno, Jupiter, and 3I Aeles. You need all that to nail the trajectory.
Okay, so if Juno makes it, what can it actually see? What instruments does it have that would be useful here?
Juno's got a fantastic suite of instruments, actually quite well suited for this kind of flyby.
Like what?
Well, it had a near-infrared spectrometer, GIRAM, that could tell us about the surface composition, maybe detect ices or minerals.
Okay, composition. What else?
Oh, a magnetometer to check for any magnetic field around the object. A microwave radiometer, MWR, which probes beneath the surface. There's also a gravity science instrument.
How would that work on a flyby?
By tracking tiny changes in Juno's trajectory as it passes the object, you could estimate its mass, which, combined with size estimates, gives you density. Really fundamental stuff.
Density, right. Important clue to what it's made of.
Definitely. Then there's an energetic particle detector, a radio and plasma wave sensor, a UV spectrograph, and of course JunoCam, its visible light camera.
So potentially great images, too.
Potentially fantastic images.
Mm-hmm.
But more importantly, all these instruments working together could paint a really detailed picture of this object, its composition, its density, maybe even hints about the environment of its home star system.
It's not just a pretty picture, it's real science about another part of the galaxy.
Exactly. Fundamental building blocks from somewhere else entirely.
No. We teased it earlier. Let's get into the more provocative side of this. Professor Loeb's involvement naturally brings up the question he raised about Oumuamua.
Right. The alien technology hypothesis.
He argued Oumuamua might have been artificial because of its weird acceleration, right? Couldn't quite explain it naturally.
Yeah, he really pushed that idea, suggesting its non-gravitational acceleration wasn't typical cometary outgassing. It was, and remains, controversial.
And now he and Hibbard and Crowell actually wrote a paper specifically asking, is the interstellar object 3I Atlas alien technology?
They did. It's quite direct.
So what's the argument this time? Why even consider it for 3I Atlas?
Well, the initial reasoning hinged on its observed brightness. Based on that brightness, if you assumed it was a typical non-reflective asteroid,
Like a chunk of rock.
then Loeb calculated it would need to be enormous, like 20 kilometers in diameter.
20 kilometers, that's huge for an interstellar asteroid just wandering in.
Exactly. Loeb argued that having such a massive rocky object ejected from another system and ending up here would imply an untenable mass supply of such objects throughout the galaxy. It seemed statistically unlikely.
So the argument was, if it is that big and rocky, maybe it's not natural.
That was the provocative suggestion. He wrote that if it were 20 kilometers across, it might have targeted the intersolar system as expected from alien technology.
Targeted us. Wow. But it's really important to add a context here, isn't it? Did they actually claim it is alien tech?
No, absolutely not. And this is crucial. They explicitly state in the paper they do not necessarily ascribe to that hypothesis.
Okay, so why publish a paper asking the question if they don't necessarily believe the answer is yes?
Loeb's rationale is interesting. He argues, look, if it were true, the consequences could be dire for humanity, possibly requiring defensive measures, though he admits they might be futile.
A bit alarming.
It is. But he also frames it as an interesting exercise and says it's fun to explore, regardless of how likely it is. It's about keeping an open mind to extreme possibilities, even if they seem far-fetched. Pushing boundaries.
Okay, intellectual exploration. But has anything changed since they published that? What about that 20-kilometer size estimate?
Yes, there's been a significant development. Recent observations using the Hubble Space Telescope.
Ah, Hubble, what did it see?
Hubble's images suggest the nucleus, the solid part of 3I Atlas, is actually much smaller. They estimate an effective radius of less than 2.8 kilometers.
Less than 2.8-kilometer radius? So less than 5.6-kilometer diameter. Much smaller than 20 kilometers.
Much smaller, yes. Which potentially undermines that initial premise based on the brightness suggesting a huge asteroid. It makes a natural explanation, like it being a comet, seem more likely if it's smaller and possibly more reflective due to ice.
So how do we find out for sure what 3I Atlas really is?
Well, there are two main ways this gets resolved. One is just waiting, as it gets closer to the sun.
If it's a comet, it should start outgassing.
Exactly. It should start sublimating ice, turning directly into gas, creating a coma and tail. If we see that, case closed, it's a comet. Maybe an unusual one, but natural.
And the other way?
The other way, the really exciting way, is if this Juno Intercept mission actually happens. Getting instruments right up close would be the definitive way to figure out its true nature.
So regardless of the outcome, natural comet or, the very unlikely alternative getting Juno there would be scientifically massive.
Absolutely massive. The data would be invaluable either way. It tells us about processes and materials in other star systems. It's a chance to, well, metaphorically touch something truly alien, whether naturally alien or otherwise.
Okay, this Juno proposal is just incredible. Repurposing an existing spacecraft, that ingenious Oberth maneuver, the chance to study an interstellar visitor up close. It's fantastic stuff.
It really highlights the ingenuity in space exploration, using the tools we have in new ways.
So wrapping this up, let's think bigger picture. What does the mere possibility, even if it's just a hypothetical exercise, as Loeb puts it, of encountering something artificial from another civilization, what does that possibility change about how we approach exploring space?
That's a deep question, isn't it?
Yeah. What are the sort of deeper questions about our own place in the cosmos that this whole deep dive makes us ask?